In this video log, we are going to talk about number system. So now, what is a number? Now, as we already know, a number is nothing but a collection of a symbol and an associated value with it, right? So this is a symbol and it has a value of 2 with it. Okay, so this is what we are familiar with. So now what is a number system? Now a number system is nothing but the techniques that are applied to operate and manipulate numbers in computers. So now we will talk about the different kinds of number system that are being used in computers. Now computers can only work with binary numbers where every data is being represented by ones and zeros. Okay, so now let us talk about the basic classification of numbers, and then we will talk about the different kind of number systems that are being used in computer, that is binary, then octal, hexadecimal, all these kind of numbers. Okay, so if I want to classify it, the types could be decimal, then we can have binary, then we can have octal, and then we can have hexadecimal. But the interesting thing about all these number systems are they are weighted. Now what does weighted means? That each and every number has 2 values associated with it, which we already know. This is place value and a face value, and that is what we know from our school days. So now let us talk about decimal number system, and then we'll talk about the remaining number system. Now decimal is the number system that we are using in our regular day-to-day transaction. It consists of 10 symbols, that is 0 to 9. Okay, these many symbols are present in it. So as it is a weighted code, so every position has a weight, that is starting from a unit place, then a 10th place, then a 100th place, and then a 1000th place. Okay, in this way. So if you just recall our systems, 231 is basically 200 plus 30 plus 1, that is 2 into 10 to the power 2 plus 3 into 10 to the power 1 plus 1 into 10 to the power 0. Now that is the base of the decimal number system, that is 10, and these are the consecutive powers. Okay, so we always start from 0 and we continue forward. Okay, so the notation that is used to represent decimal number is just like that. Okay, we put a 10 at its base. So this kind of a notation we will be using for other number systems also. So now let's talk about binary number system. So binary numbers have a total of 2 symbols, which is 1 or 0. Now it can be stated as to be on, and it can be stated as off, because as computers work with transistors which can have only an on and off situation, so every data that we store in computers is stored in some sort of binary notation. Though we talk about octal and hexadecimal, but in computers we don't actually store in hexadecimal and octal. We just use them for our own convenience and to discuss with them. Okay, now let's again, it is also a weighted code. Okay, so the positional values are 1, 2, 4, 8, 16, 32, 64, 128, 256, 512 and 1024. Okay, now these positions can be used to easily calculate or convert from decimal to binary and back and forth, so we will look at them later on. So the notation that is being used is, imagine 0101, okay, binary, so which is equivalent to basically 5 in decimal, and we will talk about how this conversion works in our subsequent videos. So it is just a basic introduction. So binary numbers are weighted numbers, and this is how computers actually store data. So now let us talk about octal number system. So in octal number system we have 8 symbols. 8 symbols. What are these symbols? 0, 1, 2, 3, 4, 5, 6 and 7. Okay, again it is also a weighted number system where the weights are basically 8 to the power 0, 8 to the power 1, 8 to the power 2, 8 to the power 3, and it keeps on continuing. So basically it is 1 and it is 8, it is 64, and it keeps on continuing just like that. Again, the notation used for representing octal number system can be 23, 8. Now the interesting thing is that if I try and write 86, now this is not a valid octal number. Why? Because 8 is not allowed in octal number system. We have up to 7. So all the numbers, all the bigger numbers that we are going to represent has to have any of these symbols, nothing out of it. So now let's talk about hexadecimal number system. Now hex means 16, so we have a total of 16 symbols. What are these 16 symbols? It is 0 to 9 and A to F. Okay, 0 to 9, A to F. Now what is A? A is basically 10. So if I try and tabulate it, A, B, C, D, E, F. So 10, 11, 12, 13, 14 and 15. Okay, so this is the biggest symbol, that the biggest value symbol that we can have. Again, if we talk about the positions, as it is a weighted code, it will have positions, that is 16 to the power 0, then 16 to the power 1, 16 to the power 2, and it will keep on going just like that. Again, the notation that is used to represent hexadecimal number is similar to, suppose it is AF16. Okay, AF16. Now let's talk about the conversion in between the bases. So let us talk about from decimal. Okay, so we will convert from decimal into binary. So to do this, and we will also try the subsequent formats of converting from decimal to octal and hexadecimal. To do this, to convert from decimal into binary, there are two methods. One is by repeated division. So imagine if I want to convert 16, which is in decimal, into its equivalent binary format. So for that, because we are going to convert it into base 2 or binary, so we have to repeatedly divide it by 2. So 2 times 8 is 16, so we have a remainder of 0. 2 times 4 is 8, we have a remainder of 0. 2 times 2 is 4, remainder of 0. 2 times 1 is 2, remainder of 0. And the order of writing is from top to bottom. So what we have, a 1 0 and a 1 and a 4 0. 1 0 0 0 and another 0. Okay, so similarly we can practice more, but there is another technique, because every time it is not possible to divide. So another technique is to use the positional value that we have seen earlier. So the positional value of binary notation is 2 4 8 16 32 64 128, and so on. So now to make 16, we can put 1 in here and all the remaining can be assigned 0. Okay, and you can add zeros in front, it really doesn't matter. So the same result that we obtained via this kind of a division can also be obtained through this kind of pattern. Okay, and when we will solve problems, we will be more clear about it. Okay, so now let's see how to convert decimal into octal. Octal, that means base 8. So imagine, let us try the previous problem only. So we have 16 which is in base 10 and we need to convert it into base 8. So now as we want to convert it into base 8, so we will perform a repeated division by 8. So 16. So 8 times 2 is 16. Remainder is 0. Right. So now we have attained a number which is lesser than 16, so we cannot divide anymore. So my answer will be 2, 0. Right. Okay. So let us try and find the representation for hexadecimal also. That means base 16. So if I'm given this particular number 16 and I want to convert it into an equivalent hexadecimal number, so again, as we are converting into base 16, so what we need to do is divide by 16. Right, so 16 times 1 is 16 and is 0, so it is equivalent to 1 and is 0. Okay, now let's talk about binary. So from binary, let us try and convert to decimal. Okay, so given a number 0, 1, 0, 1, it is in binary and we need to convert it into equivalent decimal number system. Okay, now to convert it into decimal, what we are going to do is use the positional value. Okay, so it will be 2 to the power 0, 2 to the power 1, 2 to the power 2, and 2 to the power 3. Okay, and we will add them together to get our decimal equivalent number. Now 2 to the power 0 is 1, so it is 1 times 1. Well, 0 times 2 plus 1 times 2 is 4. And 0 times 8. Okay, so now these will evaluate to 0, so what we will have is 4 plus 1 which is equal to 5. Okay, so its representation is equivalent to 5 in decimal number system. And again we will solve MCQs at the end of this log and we will get a better hold of them. So now let us talk about binary to octal. Octal representation. Now octal has 8 symbols that we discussed earlier. Now it is basically equal to 2 to the power 3. Okay, so in case of octal, what we are going to do is group 3 bits together to find the equivalent octal representation. So given this particular notation, okay, so what we are going to do, well, it is written in binary to get the equivalent octal representation. What we are going to do is group bits into a pair of 3 and we will try to get its equivalent representation in decimal. Now if you remember the positional value, so it is 1, 2 and 4. Similarly 1, 2 and 4. That means it will evaluate to 2 because the remaining are 0, so they won't be evaluated. Now all of them are 0. Now in this case all of them are 0, so 1 plus 2 plus 4, so 4, 5, 6, 1, 7. Okay, so it is equivalent to 72 in octal. Now as you can see, the benefit of using octal, and later on we will see hexadecimal also. So in terms of representing the same data in binary, we had to use a total of 6 symbols or 6 positions, but representing the same data in octal number system we only require 2 positions. So that is why octal and hexadecimal numbers are used. So now let us talk about binary to hexadecimal. decimal. Okay, so if the same binary sequence is given, okay, now what we are going to do now, hexadecimal, as we understand earlier that it consists of 16 symbols, that means 2 to the power 4. So we will group bits into a group of 4 and we will find its equivalent representation. So now if this binary sequence is given to us, what we are going to do is group a bits in a group of 4. And now the problem is that we have only 2, so we cannot do that. So let us add 2 more zeros. It will not change the value, and find its equivalent representation. So similarly, as we have done earlier, 2, 4, 8. Okay, so in this case 8 plus 2, it will evaluate to 10, right? And this will evaluate to, again let us write it down, 4, 8, it will evaluate to 3. So it is similar to 10 in hexadecimal, but the problem is that 10 doesn't exist in hexadecimal. Its equivalent notation is A, right? So it will be 3A in hexadecimal system. And we do remember that A is equivalent to 10, B is equal to 11, C is equal to 12, and in this way F is equivalent to 15, right? And we will solve more MCQs to understand it in a better way. Now let us talk about octal number system. So now let us try to convert octal into decimal number system. So if I am given, suppose 20 in octal, how I am going to convert it into equivalent decimal notation? So the way we followed the earlier examples with binary, the same technique will be applied. So it is basically 0 times 8 to the power 0, because we are converting from base 8 to base 10, and it will be 2 times 8 to the power 1. Okay, so this will evaluate to 0 and this will evaluate to 16, right? So it will finally evaluate to 16. So 16 in decimal is equivalent to 20 in octal. Okay, similarly let us try to do the same for binary. Now the interesting thing about binary is that octal is again 2 to the power 3. So again what we can actually do is get a pair of 3 out of the octal representation to find the equivalent binary representation. Okay, so now let us see again, if 20 is given in octal, the equivalent binary representation can be easily found using the equivalent representation of these in 3 bits. Okay, so 0 in 3 bits will be 0, 0 and 0, and 3 bits is the reason why we are using. Okay, and in case of 2 it will be 0, 1, 0, right? So the equivalent binary representation will be 0, 0 and 3, 0 afterwards. So this is my equivalent binary representation. Also we can perform a division method that we did in the earlier cases also, but this is easy. So now let us talk about hexadecimal also. Hexadecimal, that is 16, right? So we will convert it into decimal. Again, if you want to speed up the way I'm speaking, what you can actually do is go to the YouTube's playback option, and you can increase the speed or you can decrease the speed as per your convenience. Okay, the same technique will be applied again. So if I'm given 20 in hexadecimal and I want to find the equivalent decimal representation, the same procedure will be applied, but this time it will be 0, and because now we are using base 16, so we are going to use 16 in here, and 2 times 16 to the power 1. Okay, so this will evaluate to 32, this will evaluate to 0. So if we add them together, we are going to get 32 in base 10. Fine. So now if I want to do binary, if this is the number given, a binary, for binary we are going to group 4 bits. Okay, we are going to represent 0 in 4 bits, again 2 in 4 bits. So 0 in 4 bits will basically 40, and 2 in 4 bit will be 100. Okay, and the more you practice, you will get a hang of it, so nothing to worry. Okay, this will be the equivalent representation in binary. Okay, now let us talk about conversion in between octal and hexadecimal, and hexadecimal to octal. So hexadecimal to octal. Okay, and again it is just the idea of grouping bits. Okay, so imagine I am given a decimal number, maybe 20. I don't know why I am taking 20, maybe this is the number I really like. Okay, so now let us convert it into binary. So if I want to convert it into base 16, that means I have to group or represent these numbers into 4 bits. So 4 zeros, and it will be 1 0 0 0. Okay, so the equivalent representation will be 0 0 1 0 0 0 0 and 0. Okay, in hexadecimal. So imagine this hexadecimal number. Now what will it be? It will be basically 2 0, right, in hexadecimal. Now if I want to find the equivalent octal representation, now what I have to do is group 3 bits from here. Again, I don't have another bit, so I'll take another bit from here. It will not change the value, and then find the equivalent representation. So it will be 0, it will be, what is it, 1 2 4, right? So this position holds 4, I'll get 4 and I'll get 0, right? 0 4 0 in octal, right? And the vice versa can also be done. So if I'm given, imagine 72 is being given in octal. Now what I can do actually is convert it into binary. So let us take 3-bit representation. So 0 1 0, and 7 means 1 1 and 1, right? Now what I'm going to do is group it into 4. So these 4 bits will be grouped together, and I will add 2 more zeros to make another group of 4. Now to represent it, now what are these values? It is 1 2 4 and 8, right? So 8 plus 2 is 10, and this will evaluate to 2 plus 1 3. Again 10 is not allowed, so we will put a. So this is equivalent to 3a in hexadecimal. Okay, so we saw both, that is from hexadecimal to octal and from octal to hexadecimal. Okay, so afterwards we will see some problems of these kind of conversions, and we will solve some MCQ, and this will make our concept a bit better. Okay, and now let's solve some MCQs. So the first question is representation of the hexadecimal number 6DE. Okay, and at certain times they would give H, or they might give 16. Both of them symbolizes hexadecimal notation. Okay, so it is given 6DE. Now the positional value we have already discussed. Now this position stands for 16 to the power 0, this is 16 to the power 1, and this is 16 to the power 2. Okay, the position values are over here, and as we can see, all of them are exactly correct in terms of their positional values, right? All of them are exactly correct in terms of their positional value. So all we have to do is identify the notation. Now this 6 is also right, because it is not going to change. Only the values that are going to change is D and E. Now as we know that, now A stands for 10, B stands for 11, C stands for 12, D stands for 13, E stands for 14, and F stands for 15. Now these are the allowed notations in hexadecimal. So all we have to do is just put the values. So E, that means 14, and D means 13, right? So in where we have over here, we have 14 in place of E, and in place of D we have 13. So first one is correct. Okay, so now let's move to the next question. Okay, now question number 2 states largest 2-digit hexadecimal number. Okay, largest 2-digit hexadecimal number. Now in hexadecimal notation, we know that the largest value is held by f, that is 15. We cannot have any value more than f, right? So this combination of 2f will give us the maximum value that is possible. Similarly, that is what we know, that if I'm given 2-digit number in decimal number system, that the maximum or the largest number that I can have is 99. Why? Because decimal number range from 0 to 9, so the maximum value is 9 and the minimum value is 0. So similarly, in terms of hexadecimal, the maximum value that we can have is 15. Hence, the correct answer would be C. Okay. So the next question, the decimal equivalent of octal number. Given this octal number, we have to find its equivalent decimal notation. So what we are going to do, we are going to use the place values and the phase values of each octal representation. So what we are going to do, 5 times 8 to the power 0 plus 4 times 8 to the power 1 plus 6 times 8 to the power 2. So it will evaluate to 4, it will evaluate to 32, it will evaluate to 6 times 64. Now if we perform an operation on it, it will give us 884 plus 32 plus 5, which will give us 421 in decimal. Okay. So the next question is the representation of an octal number in decimal. Now the interesting part is that it has a point in it. Okay, it has a point in it. So we have to solve this part and finally evaluate its decimal equivalent. Again, it is not that tough. So let us start with this part. Okay, the integer part. So 2 into 8 to the power 0 plus 3 into 8 to the power 1 plus 5 into 8 to the power 2. Okay. And this part, let us just keep an imaginary point over here. So this will be represented as 1 by 8. Okay, so again, this is basically minus 1. So the positional values on the right side of the decimal point is 8 to the power minus 1, 8 to the power minus 2, 8 to the power minus 3, and it keeps on going like that. Okay, so this will be 4. So basically 1 by 4 is 25, so it is 2 plus 24, so this will evaluate to 5 times 64. Now this will be basically 320 plus 24 plus 2, so it will be 346 and 0.25, this 0.25. okay, it's clear. So it is decimal. So the answer 346.25 is number A. So our number A will be the correct answer. Okay. Now the next question is input the hexadecimal representation of 110. What they have asked is to get the hexadecimal whose representation is 1110. Now the interesting thing is that this is 4 bits, and we do know hexadecimal numbers are represented using 4 bits, right? Because 2 to the power 4 is 16. 16 means hexadecimal. So now let us evaluate what is the value of this binary sequence 110, right? So we do remember the positional values that we have seen 1, 2, 4, 8. So basically 8, 12, 14, right? 14. Now what is 14? 14 is E in hexadecimal, and we do know that, and F is 15, right? So our correct answer will be E. So if we convert E into a binary representation, it will be 110 in binary. Okay, so that's why the correct answer is E. So the next question is convert the binary equivalent to its decimal equivalent. So we have to convert 10101 to its decimal equivalent. So again, we can work with positional values. So 1, 2, 4, 8 and 16. So 16 plus 4, it will give us 20, plus 1, 21. So it will be 21 in decimal. So option A is the correct answer. Okay. The next question, which of the following is not a binary number? Is not a binary number. Now what is a binary number? A number which can only consist of two symbols, that is either a 0 or a 1. Anything else If it contains, it's not a binary number. Okay, so now this is valid because all ones, no problem. It is 101 again valid, 000 again valid, but this one is not valid because E is not present in binary number system. E is present in hexadecimal number system, right? So this is not a binary number representation. The next question, an important drawback of binary number system. So 4 options are given. Now let us try and understand which one is a drawback of a binary number system. It requires very large strings of ones and zero to represent a decimal number. Yes, it is true. So now let us check other options also. So it requires sparingly small number of ones and zeros to represent decimal number. No, it is not true. So it requires large number of ones and small numbers of zero to represent a decimal number. Now this is not true because we are not sure how many number of ones and zeros will be actually used. So this is also wrong, and obviously because one of the option is matching. Okay, one of the option is matching, so none of the above is also false. So the correct answer is it requires a very large strings of ones and zeros to represent a decimal number, and it is true. So when we talk about the base, so if we have two bases A and D, and if A is less than D, that means A will require a large number of bits, or you can say a position, to represent the same value in D. And it is true. You see, if we talk about binary number system and if we talk about decimal number system, so to represent 5, only one position is enough, but to represent the same value in a binary number system, we require more positional values, right? So we require a 1 and a 0 and a 1. Okay, at least 3 bits are required, right? So it is 1, 2, 4, right? 4 plus 1, 5. So in decimal number system, only one position was sufficient, but in binary number system, we require 3 positional value to represent it. Okay, so now let's move to the next question. Given a hexadecimal number, it is equivalent to. So, well, they have not mentioned any base, so we will look for the options to understand the base. Now, all of the options are having 8 as its base. So, what they are asking is to convert from hexadecimal into octal. Okay, though they have not mentioned it, but we can understand it from the option itself. So, we have to convert from hexadecimal to octal. Now, the interesting thing is that both hexadecimal and octal number system are basically power of 2, right? So 16, that is what, 2 to the power 3, and octal, that is basically 8, right? It is 2 to the power 3, right? It is 2 to the power 4 and it is 2 to the power 3. So because both of them are powers of 2, so we can just group them into bits and regroup them to convert it, right? So let me take an example and we can easily understand it. Okay, so 1 E 0.53. So it is written in hexadecimal, so the numbers are represented using 4 bits. Now let me write the positional value so that it becomes easy. 1, 2, 4, 8. Okay, so these are the positional value and 4 bits are used to represent each number. Now 3 means the last 2 position, that means 0, 0, 1, 1. Okay, 2 plus 1, 3. In case of 5, 4 plus 1 is 5, so we can write 0, 1, 0, 1. Now in case of E, now what is E? E is 14, right? And F is 15, we know it. So 14 means 8 plus 4 will give us 14, right? So 8 plus 4 means it will be 1, 1, 0, 0. And 1 means only 1, right? So 3 zeros and a 1. So these are the 4 groups of the number. Now if we want, we can just add a point in here, doesn't matter. So now we are going to group them into a group of 4. Okay, so we are going to group them, so 3 bits in here because we are trying to convert them into octal number system, so we have to group them in a group of 3, right? Out of 4 we are converting them into 3. So 3 bits in here, again 3 bits, so we are left with only 2 bits. So let us add another 0, it will not change the value, right? So now let us evaluate. It will be 2, it will be 4, and it will be 4 plus 2, 7, right? Sorry, 6, right? Okay, again we will do the same. In here also we are going to group 3 bits. Let us add another 0 to it. It will not change the value, so it will be 4, it will be 2 plus 1, 3, and it will be 0, right? So this is our pattern, that is 0 3 4 dot 2 4 6 in octal. Now 0 can be eliminated or can be kept, it's up to us. Okay, so which one is actually matching? 34.246. Option B is matching, so the rest are wrong. Option B is correct. Okay, so now let's switch to the next option. The octal number is equivalent to, okay, they have given us an octal number and they are trying to find its equivalent in some base. So again, similar to the earlier problem, so we are not sure about the base, so we are going to look in the options. So all of the options are in base 16. That means they are asking us for hexadecimal, right? That is 16. So the same procedure can be repeated again. So what we are going to do, 51.124. okay, I've added some space so that the numbers don't overlap. Now the interesting thing is that it's in octals. That means each and every number is being represented using 3 bits of binary, right? So we will write it accordingly, and after that we will group them into 4 bits to get the equivalent hexadecimal number. Okay, so the same positional value can be used, only 3 bits. That means 1 1. Okay, so that is 0 0 1. 2 means 0 1 0, and 4 means 1 0 0. Okay, similarly we will do over here. So it will be 0 0 1. 5 means 4 plus 1 5, right? So it will be 1 0 1, and 4 plus 2 is 6, so 1 1 and 0, right? The point was here. Now we are going to start grouping them. Now in case of the bits after the point, okay, we will start from the extreme left, and in case of the bits in front of the point, we will start from the extreme right. Okay, so 4 bits in here, 4 bit in here, a 0 is remaining, so let us add 4 bits to it, and it's all good and fine. Okay, so again we will do the same procedure. So 4 bits in here, 4 bit in here, and let us add 3 zeros, and we are done. Now we are going to calculate the equivalent representation. So this is 0, so 8 plus 2 is 10, right? And this position is only for 2, so it will give us 2. Now what is this value? 8 plus 1 9, so it is 9. 8 plus 2, it is 10, and 1. Okay, and the interesting thing is that 10 is not allowed, right? So 10 is equivalent to A, so it will become 2A0. It will become 9, okay, 1A9. So 0 can be discarded, 0 is not required. So which option satisfies? 1A9.2A. 1A9.2A. So option A is correct. Okay, the next question is about octal equivalent of the decimal number. So we have to convert this decimal number into its octal counterpart. How we are going to do that? Repeated division. Okay, so we'll repeatedly divide it by 8 because we want to convert from decimal to octal, right? So 5 8s are 14, 8 1s are 16, so a remainder of 1. 6 8s are 48, a remainder of 4. Now 6 is lesser than 8, so we'll stop in here and we will start we'll write from top to bottom. So 6 4 1. So the equivalent representation of this decimal number will be 6 4 1 in octal. That means option 1 is correct. Okay, now let us try and convert a hexadecimal number to its decimal equivalent. Hexadecimal number to its decimal equivalent. Now let us convert it. We'll take the positional value, that is 2 times 16 to the power 0 plus E. E means 14, right? F is 15. So 14 times 16 to the power 1 plus 1 into 16 square, right? So So it is 16 times 16 plus 14 times 16 plus 2. Okay, so after performing the calculation, it will evaluate to 483 in base 10 decimal. At certain times decimal is not also mentioned and it is just implied. Okay, so that will evaluate to B, 483 as an answer. Okay, so now let's move on. So they are asking for the equivalent decimal equivalent of the binary number. Okay, so to convert this binary number into its decimal equivalent, right? So what we do actually is use the positional values. So 1 into 2 to the power 0 plus 1 into 2 to the power 1 plus 0 times 2 to the power 2 plus 1 into 2 to the power 3, right? And after the point they has to be given negative powers, that is 0 times 1 by 2 plus 1 times 1 by 4 plus 1 times 1 by 8, right? That is 2 to the power 1, 2 to the power 2 and 2 to the power 3. So 2, 4, 8. Now we will evaluate it. So it is what? 1 plus 2. This will evaluate to 0, so we don't need it. And 2 times 3, 2 to the power 3 is 8. So this will be 0. So we'll have 1 by 4 plus 1 by 8. Now if we evaluate it, 8, 10 and 1, 11, right? So it will evaluate to 11.375. Okay, this will evaluate to 375 in decimal. So the answer will be A. Again, convert the decimal number into its octal representation. Fine. So now here is a point. So we have to multiply it by 8 rather than division. So in the earlier example, when a decimal number was given and we suppose 10 was given and in base 10 and we had to convert it into an octal number system, what we used to do is divide 8 by 10 and we used to get the value. But now as it is after the fractional point, decimal point, so that's why we will multiply it. So what will it become? It will become 0.345 into 8. This will evaluate to 2.76. okay, and we will store 2 for our reference, so we'll get 2 out of here. Again we'll repeat the procedure. 76 times 8 is equal to 6.08. It will give us 6. That is the whole part we are going to store and we are going to operate it again. So 0.08 times 8, so it will be 0.64. we'll get 0 out of here. Now as all of them are represented using 5 bits, so we have to get the value in 5 bits. Okay, so 0.64 times 8 will give us 5.12. and again I am using a calculator because it's a lot of calculation to perform. So we'll say 5 and we'll repeat the process. 12 times 8 and we will start writing from top to bottom. Now we don't need to perform the entire procedure. Now we can already perform a matching. So we have 2605, so it is 22605. so these are matching, so obviously option B is our answer. Okay, next question. Convert the binary number into its decimal format. Okay, similarly, so it will be 1 times 2 to the power 0 plus 1 times 2 to the power 1 plus 0 times 2 to the power 2 plus 1 times 2 to the power 3 plus 0 times 2 to the power 4. And after that all these values will be in negative power. So 1 times 2 to the power 1 plus 0 times 2 to the power 2 plus 1 times 1 by 2 cube plus 1 times 1 by 2 to the power 4. And after evaluating, so this will be what? 1 plus 2 this is 0, so both of them will just cancel out, we don't need it. 2 to the power 3 is 8, and after that it is 1, this will cancel out, this will evaluate to 1 by 8, and this will evaluate to 1 by 16. So after performing the entire calculation, okay, so this part is 11, 8 plus 2 10 plus 1 11, so half is 0.5, and 1 by 2 is 1 by 8 is 0.125, and 1 by 16 is 0.0625. okay, so we got to add them together, we will get 11, so it will evaluate to 6875, right? So the correct answer is A, not B, not C, not D. Okay, so the next question, address 200H, H means hexadecimal, contains the byte 3FH. Now H means hexadecimal. What is the decimal equivalent of 3FH? Okay, 3FH. So we have to find what is the decimal equivalent of 3FH. So we'll use the positional value, 3 into 16 to the power 1 plus F means 15, right, into 16 to the power 0. So it is 30 plus 18 plus 15, right? So 3 plus 1 4 plus 1 5 plus 1 6. So the answer will be 6. 17's A is correct. Okay, the next question is to convert the binary number to hexadecimal number. Now hexadecimal number means 4 bits. So we'll group them into 4 bits. So these have been grouped. Again we will take 4 bits from here, again 4 bits, and we have 4 bits in here. So now let us evaluate. So we do know the positional value, 1 2 4 8, right? So 3 ones, 4 5 6 1 7, right? So it will evaluate to 7, it will evaluate to 1, and this will evaluate to 8 plus 2 is 10. Now 10 cannot be used, so it is A, right? So the answer will be A 1 7 base 16. So accordingly C is correct. Okay, so now let's start with question number 19. Now over here 2 numbers are given. So the question is about to find the possible value of A. Okay, to find the possible value of A. Now B is a base and we are not also sure about it, so we'll try to find the answer from the options itself. Okay, so a best strategy would be to convert them into base 10, both of them in base 10, and then try and solve it. So to convert them into base 10, what we are going to do is 3 times 5 to the power 0. Now this is the positional value. Now 2 5 to the power 1. Now this is 5 if it's not visible, and 1 into 5 to the power 2. Okay, is equal to, again B is our base over here, so A times B to the power 1 plus 3 into B to the power 0, right? So now let us simplify it. So it will be 3 plus 5 plus 25, right? 5 times 5, 25, and it will become A B and plus 3, right? Because it will evaluate to 1. So let's remove 3. So what we are going to get is, okay, so well, it is not 5, it is 10 actually, right? So it will be 10. So it will evaluate to 35 AB, right? Now let us try and guess what could be the possible values of AB, right? So the possible values of AB, because it is 35, so the factors possible are 1 35 and 7 5, right? Because if you multiply them, both of them will evaluate to 35, right? So now let us think about the values, right? So if A and B, right? If A is 1, B is 35, obviously we are going to get 35 as it is, right? And the reverse is not true. So if I write 35 1, it is not possible because B is the base. Okay, so 35 means we can have a value from 0 to 34, so that's why this is correct. But this doesn't hold because with the base of 1, the only value you can have is 1, you can never have a value of a as a 35, so this will never work. So now what about 7 and 5? So now imagine, let us write it again, a and b. So 7 and 5 is not possible, because again with a base of 5, or 5 is the number system, so you can have 0 to 4, that is 5 minus 1, 4. So these many values, so it is not possible. So what about 5 times 7? Yes, it is also possible if you think about it. So with 7 you can have value from 0 to 6, so 5 is included, so it is all good and fine. So the possible values are 1 and 5. But the interesting thing is that 5 is not present in the option, so A is our answer in this case. Okay, so don't worry about the handwriting. I am going to add a PDF of all the questions and along with few extra questions for your practice in the description. Okay, the next question is to convert this string into base 32, right? So well, obviously we haven't seen base 32. Now how can we prepare base 32? Now 2 to the power 5 is 32, right? So what we are going to do, we are going to group bits into 5, right? So 5 bits will be grouped into 1 and the equivalent number will be used. So as they have not mentioned any base, so we can consider them to be in a decimal format, right? Because that is what happens by default. So let us take 5 bits, 1, 2, 3, 4, 5, right? So these will be occupied in 1. Again 1, 2, 3 and 4, 5, right? Let's group them together. 1, 2, 3, 4 and 5. Okay, 1, 2, 3, 4, 5. Again 5. Now let me write the positional value. 1, 2, 4, 8, 16, right? So this will evaluate to 16. This will evaluate to 4 plus 2, 6 plus 1, 7. And now this will evaluate to 4. 8 plus 4 will give me 12, and plus 2 will give me 14. And what about this? Now this is 16, and 16 plus 4 is 20, and plus 2 is 22, right? So we can simply identify that option 1 is correct. Okay, so now let's go for the second question, and it is a bit tricky, similar to the earlier question. Now here they have said the C stands for 12, right? And obviously it is a hexadecimal number system. Now they have asked what could be the value of A and B, right? So now because there is space over here, so let us start it from here onward. A and 1 and a B, and it is in base 8 and it is in base 16, right? 12 C 9. Now let us actually, so it is not 12, okay, it is 1 and 2 because 12 is not allowed in hexadecimal system, right? And C, what does C evaluates to? Now A is 10, we know that, and B is 11, so C becomes 12. So this is 12, and in case of hexadecimal number system we need 4 bits, right? And we know about that. So 1, 2, 4 and 8. Now 12 means 1, 1, 0, 0, right? 8 plus 4, 12. So now let us convert it into its equivalent decimal notation. Let us convert all of them into their equivalent binary notation. Okay, equivalent binary notation, and then we will group them in 3 bits and we will find the value of A and B respectively. Okay, so 9 means 8 plus 1, 9, right? So 1, 0, 0, 1. What about C? C is 12, that means 8 plus 4, 12, that is 0, 0, 1, 1. 2 means 0, 1, 0, 0. That is the value of 2, and 1 is 1, 0, 0, 0. Right? Now let's start grouping it into a pair or a group of 3. Now let's club them in a pair of 3. Okay, so 3, again 3. We are clubbing them in a group of 3 bits. Again, let us add 2 bits, doesn't matter. So now let us equate. So this is B, right? From this notation we can easily understand this is 1, this is A, this is 1, this is 1, and this is 0. So we can just simply remove it. So the possible value of A is 0, 1, 1, and possible value of B is 0, 0, 1. Now this evaluates to 2 plus 1, 3, and this is 1, right? None of the option match over here, so the answer will be none of the above. Okay, now let's move to the next question. Okay, and the value of x and y. Now they have given an expression and we got to solve it to find the equivalent expression for it, right? So it is x 5 6 7 and 2yx 8 and 7 1 yx, and everything is in octal notation. Okay, now to convert it or evaluate the value of x and y, so let us convert it into equivalent decimal format so that we can perform the normal addition multiplication operation on them. Okay, so what we are going to do is write them in the positional value format. So we have 0, 1, 2 and 3, right? So it will be x to the power x into e to the power 3 plus 5 into e to the power 2 plus 6 into e to the power 1 plus 7 times e to the power 0 plus, okay, this part is 1. Now we are going to write this one. So 2 into e to the power 3 plus y into e to the power 2 plus x into e to the power 1 plus 5 into e to the power 0, which is equivalent to, now the same procedure will be repeated for this also. 3 times x to the power 2 plus y into e to the power 1 plus x into e to the power 0. Okay, so after evaluating the entire thing, we are going to get x 512x plus 320 plus 48 plus 7 plus 1024 plus 64y plus 8x plus 5 is equal to, if we evaluate the entire sequence, what we are going to get is 3, 5, 8, 4. Now obviously I have pre-calculated this, and 64 plus 8y plus x. Okay, so after evaluating, because we don't have space, so let me write the pre-evaluated value. So after solving the entire expression, we are going to get 519x plus 56y is equal to 224. Now we got to look out of the options which one will satisfy. Now if we put 4 in place of x and 3 in place of y, it will evaluate to 519 times 4 plus 56 times 3, and this is basically equal to 224, right? So it matches. So our correct answer is 4 and 3. So this will be true. Okay, option A is correct. Obviously we could have performed addition in base 8, that is octal addition, but as we have not talked about octal addition, so that's why we did it in decimal format. So yes, it became a bit complicated, but it's always a good strategy to use a generalized representation or generalized method. Fine. So the next question is the number of ones. Okay, the number of ones in binary representation of the decimal expression. Okay, so this is the decimal expression, and from the base or the positional value we can understand it's a hexadecimal number, right? So as it is 16, so it is hexadecimal number. So we have 9 7 5 in here, so that means 9 7 5 3. It is written in hexadecimal, and we have to find the equivalent binary representative, that is a number of ones in the binary representation. So let us convert it into binary. So it will be 1 2 4 8, right? That is the positional value. So 2 plus 1 3, so 0 0 1 1. 5 means 4 plus 1 5, right? So 0 1 0 1, right? 7 means 4 plus 2 6 plus 1 7, 0 1 1 1, and 9 means 8 plus 1 9, so 1 0 0 1. Okay, now it is just a simple matter of counting the number of ones in here. Okay, so 1 2 3 4 5 6 7 8, 9. Okay, a total of 9 ones, right? So the correct answer is 6. Okay, so here our lecture on number system concludes. So I've included some very complicated problems to very simple problems also. So hope this will help you, and do subscribe to the channel for more videos, and do give your comments about what we can include next. So I think the next video will be about the codes. Okay, the codes present in digital system, like BCD and gray codes. Okay, these kind of weighted and non-weighted codes we will discuss in the next video. Okay, till then, thank you.